Hi, my name's Brett Allison. I'm glad that you have decided to go through this course. We want to talk about managed storage system architecture today. These materials have been put together by myself as well as Dr. Jobert Houtekamer. Hope you enjoy them. So what I'm going to do in this presentation is to walk through some of the history and the trends in disk technology so that the listener can gain an appreciation for where we've been and where we're going. I also want to talk through the different types of storage system components, and that's going to cover sections on the different disk technologies, RAID, physical components within a controller, as well as the logical components. We'll also take a look at what thin provisioning is, at least for some of the platforms. And we'll also survey automated tier solutions for several platforms.
In this section, we'll look at the trends in enterprise storage system technology.
In 1956, when IBM introduced the RAMAC 305, it had a whopping capacity of 5 megabytes. It took up an average size office and it cost $50,000. Today we're finding very dense drives available for both consumer and enterprise. The picture of the HDS 10 terabyte drive is shown on the right. This is just to give you an idea where we've gone in terms of the density and capacity of the drives over the last 50-60 years. So the areal density trend has been 20% compound annual growth rate since the first drives were introduced. There has been some slowdown in the recent years, but the current rate should continue for a number of years. The average seek time trend, on the other hand, has simply not progressed as fast as the areal density trend. So instead of 20% for the areal density, we're looking at something between 2 and 5% for the seek time. There do not seem to be any big improvements in spinning disk drive technology in the near future. So we don't expect this to really get much better. So while the spinning disk technology is not improving in the seek time, and the overall latency is not really getting much better, we've seen massive improvements in the areas of flash technology. And what we've seen is basically a double every 2 years in terms of the number of random IOPS per SSD. And we expect this trend to continue for some time into the future. This chart depicts the interface roadmap for fiber channel over Ethernet, iSCSI, and SAS. And really, these are fairly recent trends. There's not a lot of data on them. They tend to double every 3 or 4 years. And what we're seeing is kind of a convergence in terms of the trends, in terms of throughput. And the speed that we're talking about now for a single interface is between 25 and 40 gigabits per second. So really there's quite a few trends that are happening in the enterprise space right now in terms of disk technology. The most important thing is that SSDs and flash-based arrays are becoming pervasive in enterprise computing. We're seeing more and more of these at our customer sites, and we expect this to continue as the cost associated with the SSDs and the performance continues to improve and the costs continue to get reduced. We are seeing that spinning disks are getting bigger but not faster. This is going to continue. We're going to continue to see more and more auto tiering within the controllers. It's fairly pervasive for enterprise controllers, and that does allow the enterprise controlling space to leverage the fast SSD and flash technology along with the nearline large areal density drives. We're seeing some pressure on the access density with deduplication. So as fewer bits are kept, but they're more active, we do see an increase in the access density. We also see that SSDs are, we've seen that SSDs are fast, really fast for certain workloads, particularly random read and random read miss workloads. And the auto tiering are technologies are taking advantage of those as well. But we also see that they're not general purpose devices. So they're not necessarily better for everything. We see the other trend that I talked about recently was the interface speeds are definitely getting faster, and we're I'm not seeing that at least in the enterprise space, in production enterprise space, that we're actually hitting interface constraints too much. Although that will continue to be a cat and mouse as the speeds of the interfaces get faster and we continue to put more data through to the flash and SSDs. We also see virtualization of servers and storage continuing. That leads to simplified management in some ways, but also in other ways there's more complexity in the environment. So better tools with better visibility are required. And then encryption is continuing to be an important trend, and that is just a feature that is expected now in the enterprise disk controller space. And it does add overhead. Of course, the computers are, the controller processors are getting faster, so they seem to be keeping up with that kind of thing.
In this section, we'll look at the disk technology basics.
What we have on this slide is a picture of a hard disk drive. In this case, it's an IDE interface. So if you look on the side closest to the right, you'll see the connection interface, and then usually there's some jumper settings there and a power connector. And then on the top side, we have some important pieces, and we have platters, and that's what you see, the circular large circular areas of platter, and then you have the spindle, which spins the platters around, and the platters rest on the spindle. And then you have a head and an that does the reading, and an actuator arm that moves the head into position to read the data off of the drive. And so when you think about the different mechanical things that have to happen here, you have to rotate the platter to get the right track underneath the head, and then the head has to move in and out from the outside of the platter to the inside, possibly moving the whole length of the disk, on average half of the disk, to get into the right location to read the data. And so all of those things take an approximately a few milliseconds. So when we talk about the speed of hard disk drives, no matter how fast they are, as long as there's some mechanical components involved, and no matter how smart the firmware is and the caching, it still takes a few milliseconds to get data off these drives. And depending on how much data you need, and the type of access, it's fairly lengthy. This picture is of an SSD flash device. In this case, you can see on it's a board. It's not a spinning disk. It doesn't look anything like a disk. It looks like any kind of board that you would put in on a motherboard or main board. And it has a series of chips. Now these chips have NAND-based flash memory on them. And so I guess the obvious thing is that there's no spinning disk, so access times are much faster. There's no seek time, there's no rotational latency, and no moving parts to fail. So the other thing about that is, because there's no mechanical movement, there's a reduced energy requirement, and the heat from these is lower. So there's no longer any such thing as a cache unfriendly workload on these types of devices. So let's compare the HDD and the SSD based on the drive performance characteristics. So they both have protocol that's required to decode the commands depending on the interface and the type of protocol that's being used. In terms of the HDD, there is seek time for the position of the head, and in terms of the SSD, there's no seek time. In terms of rotational latency, waiting for the record to pass under the head. HDDs have these, SSDs don't. In terms of data transfer, they're both going to have to transfer data. And in terms of sequential preload caching, they're both going to have algorithms to try to prefetch data that they anticipate will be requested soon. The other thing about the access, they're both going to optimize it, but for HDDs, it's going to be for speed, whereas for SSDs, it's going to be for wear. Service times are another way to look at the drive capabilities. I have nearline drives here, and then 10 and 15K spinning drives, as well as SSD. As we discussed before, the SSDs do not incur any seek or rotational latency, so the only thing they have is protocol overhead, which tends to be about 0.2 milliseconds. And as you look at the others, you can see there's a vast difference. Obviously, the 15Ks can be under 5 millisecond depending on how it's being accessed and the firmware around the drive and the optimization that's taking place. 10K RPMs tend to be between 6 and 8, and SATA nearline drives tend to be between 10 and 13 milliseconds depending on the drive and how intelligent the algorithms are.
To summarize disk technology, disks are either mechanical or memory-based. They have different form factors, but the current standard is a 2.5-inch drive length. Spinning hard drives suffer from mechanical requirements of seeking and the rotational latency that SSDs do not. In the future, flash-based memory drives will become the predominant form of near-term persistent storage, and it is highly likely that the form will condense significantly. In this section, we'll look at the basics of RAID technology.
The term RAID is used to describe a redundant array of inexpensive disks. Its intention is to improve or increase the availability of disk infrastructure. So today we think it would be unthinkable that applications would have to be taken down for planned or unplanned maintenance, but in 20, 30 years ago that was quite the norm. And really, transactions arriving from the outside couldn't be recovered once they were lost. So RAID was invented, and what this does is it provides the ability to significantly improve the availability, while in some cases also improving performance by distributing the workload more evenly across a number of disks. In this section, we're going to talk about a few different types of RAID that are common in today's infrastructure. In this slide, we're going to take a look at RAID 1, or mirroring. In the illustration on the left, we have two different drives. We've got a primary drive and a secondary drive. The drive is composed of several volumes. In the example, we have volume 1A on the primary and then 2A on the secondary. So the 2A should be an exact duplicate of the data that's on 1A. So what happens in the case of a read, the read takes place from the primary drive. And that's essentially the same type of mirroring logic that is used for any mirroring implementation. The read comes from the primary drive. So a read has a single I/O associated with it, whereas the write, they have to go to both drives. So for a write heavy workload, there's going to be 2 IOs for every write. There's no striping in this simple RAID 1. The read build process would be very quick because you're copying data from, say, the secondary to the primary if the primary fails, or from the primary to the secondary if the secondary fails. There's like I said, read, there's no overhead. Write, there's a 100% overhead. In this slide, we're going to talk about RAID 10. RAID 10 is very similar to RAID 1 mirroring. The difference is that RAID 10 is striped and mirrored. So what we have is on the top row 3 separate disk drives with 3 volumes on them, 1A, 1B, and 1C. And then on the bottom row we have three different disk drives with three volumes on them, 2A, 2B, and 2C. So 2A is a copy of 1A, 2B is a copy of 1B, and 2C is a copy of 1C. So again, the overhead for reads, there is none, and the performance should be good. The IOs are distributed evenly across the spindles, and as a general rule, in terms of the write overhead, it's the same as RAID 1. You have two places where the data is stored, so you have to write it two places. So for every single write IO, there are two physical disk transfers. And in terms of availability, in this configuration, you could lose 3 disks as long as they're not both the primary and the secondary copy of the data or the volume.
One of the benefits of RAID is that it intentionally, by design, distributes the I/O workload across the available devices. So in the top left picture, I have a series of disks, and then I have some callouts that indicate that there are some number of IOs on different LUNs that are on different disks. So if you have a one-to-one relationship between a logical volume and a physical volume, unless those volumes are somehow managed volumes where you distribute the IOs evenly, you can get a lot of imbalance in the workload across the different volumes. And if you don't spread that workload evenly across the disks, then you can get into a situation where one disk is heavily utilized and the others are not. What RAID does is it distributes the workload evenly across the disk. So in the case of the lower picture on the lower left, I see that I have 4 different physical disks and I have some number of volumes, and if I have 100 IOPS total, I'm going to get approximately 25 IOPS across each of them for a RAID 10 rank. So it may not be an exact balance. There may be hot spots for single tracks, but it will be close, and it does a lot better than just a bunch of disks. And the larger the RAID groups, the better the distribution is of the workload typically.
RAID 5 is designed to rotate data and parity across the available disk drives. If you lose one disk drive in a RAID 5 parity group, you'll be able to recover the data and the parity. If you were to lose 2 disk drives in a RAID 5 parity group, you would not be able to recover. In the next few slides, we'll talk more about the different performance aspects for using RAID 5. Let's take a look at what happens when we have to rebuild a RAID 5 disk. So to estimate it, the time, what we'd want to do is we'd want to take the usable capacity of the drive divided by the average peak sequential I/O rate multiplied by the peak sequential transfer size. So we're going to assume in this case that the rebuild algorithms are smart enough to do sequential I/O and that they can sustain 150 IOs per second for the sequential type of activity, and that they can maximize the data that's written by using a fairly large transfer size. So let's take a 2 terabyte drive, which is roughly 1.7 terabytes of usable, or 1,700,000 megabytes, and we'll look at a drive capacity of 150 IOs per second, a transfer size of 256 megabytes, and a rebuild time that would take approximately 44,270 seconds, or a little over a half a day. So you have a half a day that you're running the rebuild for the drive. What happens if another drive failure occurs during that rebuild? And that assumes that there's no additional new I/O accepted during the rebuild, which is not usually the case unless you're in a development environment. So there's obviously a half a day there. If you start looking at larger drive sizes or looking at smaller I/O transfers per second or smaller disk transfers, you're actually looking at much longer periods. So this is a very conservative estimate. I've heard shops where rebuild of RAID 5 groups can take multiple days. Let's take a quick look at the RAID 5 random write. Step 1, read the old data block. Step 2, read the old parity block. Step 3, compute the new parity. Step 4, write the new data block. And step 5, write the new parity block. So there are 4 disk accesses required for a single write action. But this only applies to the random I/O, as we'll see in the next slide. Let's look at sequential write operations on RAID 5. On RAID 5, the random writes are very expensive because there's 4 disk accesses. But on sequential writes for RAID 5, there can be fewer disk accesses, and this is why. For a write operation, if the data that's being written sequentially already exists in cache, it's simply a matter of computing the parity, writing the data on disk, and writing the parity on disk. So now we're talking about 2 disk operations for a streaming sequential I/O versus 4 for a random. And this is regardless of the number of disks. Another type of RAID configuration is RAID 6. RAID 6 has an additional parity drive so that it can sustain a dual drive failure. So for any RAID 6 RAID group, you can lose 2 of the drives and still recreate the data in parity. When might this happen? Well, this can happen if you have a second disk drive fail during a RAID rebuild, so some kind of hardware error. You could also have an operator error where you pull the wrong disk during a rebuild. So the real reason for RAID 6 is that as the disk drives were starting to get bigger and people wanted performance of larger RAID group sets, they were experiencing double drive failures when the drive rebuild or the RAID group rebuild was running, which for larger drives can take a week or 2, sometimes longer depending on the type of drives and the size. And so what was happening is there was a pretty big time period when disk drives were exposed. So the idea of the RAID 6 is to be able to perform RAID rebuilds and have the resiliency required to sustain 2 drive failures. So RAID 6 uses 2 parity drives, and the parity floats in the rank. It's not like you have 2 drives that are dedicated. The parity and the special parity will float. So you have P in this case, which is the normal parity, and Q, which is the special parity. And basically Q allows us to place the failing bits on the proper disk. P and Q can protect up to 253 data disks from dual failures at the byte level. Now let's look at the RAID 6 random write. So it's similar to RAID 5, except now we have 2 parity disks. So we actually have to do 3 IOs just to read in the data parity and the special parity. Then we have to compute the new parity, and then we have to write out the new data block, the new parity block, and the new special parity block. So random write IOs are going to take 6 disk accesses for a single random write. So if you have a very highly random write workload, especially if it's intense at all, the RAID 6 is not going to perform well. So we looked at the individual RAID technologies, the way they do striping and parity, and what I want to do here is take a step back in this slide and take a look at the overall enclosure and just get an idea of what can happen when you have these different technologies, which by themselves are not bad, but if you start to micromanage the controller across the disk enclosures, you have different types of RAID groups. What can happen is you can have very hot spindles in some drive enclosures, and other drive enclosures you can have almost no activity. So there has to be something better. So another option is to use a distributed RAID, something like what the IBM XIV uses. In this case, they cut each volume into 1 megabyte partitions or chunks, and they spread these evenly across all of the available disks. This ensures that there are no hotspots, so there's no tuning required, and hardware can be added and removed dynamically. This ensures that you have a very highly available system. So when you have one or more than one disk drive failures, the parity and the data can be automatically calculated and redistributed across the existing disk drives, and it also ensures good performance. To summarize RAID, it can improve reliability and performance while reducing skew at the expense of capacity. So the more space that you need to use to improve the availability, the more space you lose for usable space. The primary disk technologies still in use in most enterprise systems are RAID 1, RAID 10, RAID 5, and RAID 6. RAID 6 roughly doubles the I/O workload on the back end on average, and in terms of random writes, RAID 6 has a overhead of 6 IOs per random write. So it's very write overhead intensive. Another thing to consider as we continue to see larger disk drives is the increase in rebuild time required and how much longer can we use the traditional RAID technologies and still have reasonable rebuild times. So those are some things to think about and understand with regards to RAID technology. In this section, we switch our focus from the RAID technology to the physical components within a storage controller. In this slide, we're going to look at the traditional disk storage system architecture, and those would be for controllers that are like the IBM DS8000 or the HDS G1000 or the rebranded HP P9500. Both feature dual active controllers and front-end adapters that connect to other storage systems for copy services or to hosts. There are disk adapters on the backside that connect cache and disk together. The cache memory is required to provide good performance for reads if there's read hits and for servicing fast writes. Also, there is a high-speed interconnect bus or switch between the cache in the front end and the cache and the processor and the cache in the back end. In all of these cases, there's a backup battery and 2 copies of all data are kept in case any of the modified data is lost in transmission. So the bigger, the more high-end controllers tend to have larger caches, more cache options, more bandwidth, more options for RAID and some of the other features, and more redundancy. For enterprise storage controllers, there's a couple different approaches to cache and processors. For the IBM implementation, for the DS8000 anyways, there's a large centralized cache and NVS management. For the EMC and HDS, the cache is shared between the engines or processors, but it's distributed. In any case, the cache is used to store recently used tracks and records, recently written records, preloaded tracks for sequential read operations, also some form of track descriptor tables to facilitate write operations without a disk access, and then also the asynchronous copy information. Most traditional controllers have devices for connecting to hosts. These are generically called host adapters, although in some implementations they have other names. But essentially they provide the same task, and that is to provide connectivity between the storage systems and the hosts or other storage systems. So what they do is they support the fiber channel or iSCSI protocol, in some cases enterprise FICON, and they provide handling for the FICON and fiber traffic. Within the generic type of host adapter, there's a few different components. There are fiber channel protocol conversion engines. There are processors or a processor and buffers. And there are also data mover ASICs that are specialized processors just designed to move data in and out. In terms of the ports that are in front of the fiber channel protocol engines, these are typically rated at between 4 or 8. Some of the newer controllers are being rated at 16 gigabits per second. And it should be noted that some systems like the EMC VMAX, the HP 3PAR, and the IBM SVC use the processor cores from general purpose onboard processors to do the processing required by the host connecting devices. So when we talk about the back-end adapters, we're of course talking about the components that connect the cache to the disk drives. The responsibility of the back-end adapters is to provide data movement activities, to provide RAID calculations, and that's accomplished through some logic that's embedded usually into a specialized chip or ASIC. Sometimes there's specialized processors, and there's usually some kind of cache and buffer for buffering the data in and out from the cache, from the main cache. And then for connectivity to either the back-end drives, usually they're either on SAS or fiber channel connections. The VMAX architecture from EMC is slightly different than the IBM DS8000 or HDS G1000. The way that it differs is it uses a horizontal clustering technique whereby you can attach up to 8 engines that consist of 2 directors each. Within each director, there's 8 host ports, 8 disk ports, 64 gigs of cache, and dual quad-core processors that are connected together via 2 virtual matrix interconnects. The disks and the host ports are the processing that happens to move the data in and out from the host and from the disk to cache happens via the cores on the processors as opposed to specialized ASICs. In case of failure of any component, there's 2 copies of the data kept, of all data, to prevent loss. The HP 3PAR platform is different enough that it lends itself to a unique slide. It consists of up to 8 nodes. Each of these nodes contains a multi-purpose fiber channel port used to connect to either host or disk. There's also 4 gigabytes of the cache dedicated for control and metadata activities, and 12 gigabytes, which scales up to 64, for the data cache. One thing that's different about this platform is that it does have some specialized ASICs. There are 2 specialized ASICs for data movement and cache management. And the cache memory scales linearly based on the number of nodes. A high-speed interconnect is used for connecting the cache to the other components. And there's a battery backup, and 2 copies are kept so that if there's any data loss, it can be recovered. Another type of architecture is a grid-based architecture, such as the IBM XIV. The IBM XIV consists of up to 15 interconnected modules. Each of the modules contains its own processor, memory, disk drives, and optionally SSD drives. And then there's some interface and data modules, which contain interfaces between the different other modules. It uses InfiniBand high-speed interconnects, and there are multiple backup power systems. The idea is that if any single module failed, the system would continue to operate normally. Another type of storage architecture is the in-band block virtualization appliance. A couple examples are IBM's SVC and EMC VPLEX. Both of these used fiber channel adapters to connect the controllers to hosts or other storage systems, as well as each other. These are typically done in pairs, so you'll have a couple of nodes that worked in tandem. They're usually active nodes, and they work to communicate from the host to the back end. Cache memory is used to provide good performance and to provide information for replication services. The traffic in these cases all happens over the fiber channel network. And just like the more traditional storage platforms, there are battery backups and 2 copies of essential data to avoid any kind of loss. In this section, we're going to be talking about volume management and auto-tiering technologies. The first platform we'll look at is the IBM DS8000 and its logical components. These are storage pool-based volumes. So if we look at the picture on the right, we have a series of disk drives, 1 through 8. These disk drives are formatted into some kind of RAID group. So in this case, we have RAID group 1 and RAID group 2. And those RAID groups are provided to an extent pool, otherwise known as a storage pool. Within the storage pool, the extents are divided up into smaller 1 gig partitions, and they are assigned to volumes, and they are made host addressable. The point of this slide is to just show that the extents from the extent pool and assigned to the volume are distributed in a round robin or striped fashion across the available RAID groups to distribute the I/O evenly. So the IBM SVC Volume Management schema is very similar to the DS8000. The main difference is that you have externally managed storage on the SVC. So the RAID groups on the external storage systems are created, and then volumes are created on the RAID groups. Usually it's a 1-to-1 relationship between a volume and a RAID group. And then those volumes are imported into SVC as managed disks or managed volumes, and then they're provided to a storage pool. Now, the storage pool then consists of some amount of space that was provided to it by multiple LUNs, and within that, it's broken down into 1 gigabyte partitions or extents. And then those extents are provided to the host. Now, on the back end or the managed volume side, the default way that it works is that the extents are striped across the LUNs. So the goal of that is to improve the distribution of the IOs across the available storage. The IBM Easy Tier solution works on all of the IBM enterprise platforms. And the goal is to take advantage of different types of disks within a controller. So let's say you have a 3-tier hybrid pool that consists of SSD, fiber channel spinning, and nearline drives. And the goal is to put the hottest data on the fastest drive. So if you had SSD, obviously that would be the fastest drive. So what happens is that a process runs, it collects statistical data about the extents, so how much read-miss activity is happening on the extent level. That data is collected and analyzed and sorted, and the hottest extents are then, there's a plan created to migrate the hottest extents to the highest tier. And so then the next step is that the extents are actually migrated to the right tier. And extents that are way down on that list in terms of activity would be demoted to a lower tier. In the example shown, I'm just showing a 2-tier system, but you're going to have, in most of the hybrid pools now, they're going to be 3-tier. And the idea with Easy Tier is that you set it and forget it. You don't worry about managing it or making sure that it's working right. You just hope it runs well. A couple tips. You want to make sure that it's analyzing during the right time frame, and there are some configuration options to set that. The other thing is you want to make sure that if you do the if you do run Easy Tier, you need to have some space available within the pools so that you can do the migrations effectively. If you don't have any free space, Easy Tier is not going to work. It's kind of like gridlock on the freeway. You need to have some free space. All right, let's talk about EMC's volume management. So the most basic way to look at this is you have a set of physical spindles. You create from those physical spindles some data devices, and those data devices are provided to a thin pool. Now the thin pool is going to consist of a single disk or RAID type, so maybe it's a fiber channel thin pool, and then from there you're going to be creating host addressable volumes, or thin volumes, or thick volumes. So let's talk about EMC's auto-tiering technology. So within the VMAX, there is something called the Fast VP. And the way that it works is you have tiers. Now, these tiers they're like the thin pools that are dedicated to different disk types. So you have a thin pool that's maybe the EMC flash device tier, a thin pool that's the fiber channel tier, and the thin pool that is the SATA tier. So these become your tiers. And then you have policies that describe how much capacity can be allocated to different tiers. And then those policies are assigned to a storage group. So you can specify capacity maximums per tier, and those can actually be as much as 100% for each of those policies. So you could have a policy with 3 different options in it, flash, fiber channel, and SATA, and say 100% for each. And what will happen in that case is that the Fast VP will decide what it needs to do without regards to capacity. So it will try to put the right blocks of data on the right tier. So that's the default would be to set it up that way, or the best practice would be to set it up with 100% for each and then let it go. Now you may have situations where you have certain storage groups that you want to have preferential treatment for certain tiers, or you might want to limit how much capacity could actually be taken by certain storage pools. So that's when you would use the capacity maximums. Let's talk about HDS Volume Management. So you'll have disk drives of different device types. So SSD drives will be formed into SSD RAID groups, fiber channel will be formed into fiber channel RAID groups, and nearline will be formed into nearline RAID groups. And then a special volume will be created. It's called a pool volume. And the pool volume will take space from a single device type. And then you can create a hybrid dynamic pool, or just what they call a dynamic pool, from the pool volumes. And so the dynamic pool will then consist of volumes taken, specialized volumes called pool volumes, that consist of dedicated device types. And then from there, you'll create a virtual volume. The virtual volume can actually have pages that consists of data that resides on different types of disk from the different pool volumes that are part of the dynamic pool. The HDS auto tiering is called Hitachi Dynamic Tiering, or HDT, and its goal is to optimize the distribution of IOs across the available disk resources. It typically consists of 3 tiers: the fiber channel, the nearline, and then the flash or SSD at the tier 0. And for a dynamic tier volume, it will identify those hot or hottest extents and sort them based on a heat index or a heat map, and place the hottest data on the the fastest drive blocks. So the idea is that you would just set it and forget it. It does have the ability to do all of the migrations automatically, but a storage administrator can change the auto tiering to be manually, and to manually initiate migration between the tiers. Let's take a look at the HP3PAR volume management. The way it works is you'll have SSDs, fiber channel, and nearline devices as your disk drives, And within those, you'll have chunklets that actually come straight from the physical disk, and they're treated like mini disks, those little chunklets. Those chunklets are grouped together to form logical disks. Now, a single logical disk will consist of chunklets from one disk device type. So you'll have SSDs, fiber channel nearline with chunklets. Those chunklets will be grouped together to form SSD logical disk, fiber channel logical disk, and nearline logical disk. And then a common provisioning group, which is similar to a policy, will group similar logical disks for provisioning. So you'll have like a CPG for SSD, a CPG for fiber channel, and a CPG for nearline. And then a virtual volume will be addressable to a host, and it's either tiered or non-tiered. HP3PAR's auto-tiering technology is called adaptive optimization, and it consists of common provisioning groups that are assigned a policy or an adaptive optimization policy. So let's take the example where we have 3 different types of CPGs. And a CPG underscore SSD, which has the SSDs in it, a CPG underscore fiber channel, which has the fiber channel drives in it, and a CPG underscore nearline, which has the nearline logical disks. So let's look at one of the policies. So let's call the policy gold. And in the gold, we have a tier 0 CPG, which is the SSD. And we also have a tier 1, which is fiber channel. And we have different modes that we can set to instruct adaptive optimization how to behave. So if we have the mode set to performance, as in the case of the gold tier, it's going to try to move as much I/O to the SSD tier. In the case of the silver, we have a tier 0, which is the SSD, and a tier 2, which is the nearline. And I've set in the example the mode to balanced. And what this does is it tries to distribute the IOs evenly across the SSD and the nearline based on their capabilities and the amount of space that's available. And then let's look at an example where we have a bronze adaptive optimization policy, which consists only of the fiber channel and the nearline CPGs. And we set it to cost. And what it's going to try to do is to move as much as possible to the nearline CPG. This all happens under the covers. You're not really supposed to see what's happening, although they do give you some flexibility in terms of influencing the behaviors. And I described the modes there, the performance, the balance, and the cost. It's also good to know that you can set warning limits, and so you can actually influence how the adaptive optimization behaves, and by setting CPG warning limits for capacity. It's also good to note that there is a little bit of overhead, so when you schedule your AO policy to run, there is a bit of overhead on the front end adapters or the ports. And so you'll see as the data is migrated between the different CPGs, it's going to consume some resources on the controller. So one of the important concepts to understand when you're going about configuring a controller with different disk tiers and setting up auto tiering is to understand the locality of reference, or the skew curve. What the skew curve does is it describes the relationship between the locality of the IOs per second and the capacity that's available. So the steeper the skew curve, the more cost effective your implementation will be, and the more flat the skew curve, the more costly the implementation will be, and the less likely it will be to take advantage of the nearline and the SSD. So let's look at a couple of the examples in this base underscore ESX underscore AO skew curve. So we have down below on the legend, I have 4 different series. I've got the CPG underscore 450 gig RAID 5 3+1 AO online. So that's my 450 gig drives. I've got the That's for the online window. I've got CPG 900 gig RAID 6 for online, and then I've got a CPG 450 RAID 5 AO batch, and then a CPG 900 gig RAID 6 AO batch. So what I have here is this base ESX adaptive optimization, and I'm looking at the two CPGs for two different time periods. So if we look at the green and yellow lines, these are basically the same lines, and it's the CPG has the same behavior during the online and the batch, and it's a fairly flat skew curve. If we look at the 900 gigabyte activity, it's a very steep skew curve. So the steeper the curve, the more likely we are to take advantage of some SSDs and really improve performance. And let's look at the chart itself. On the y-axis, we have the percent of the IOPS. So, for example, if we're looking at the 900 gig RAID 6 orange line, 80% of the IOPS happen, and if we look at that on the y-axis, within about 4% of the overall capacity. So that kind of a skew would do well on an environment where you have lots of the large, drives and a few of the SSDs, because you could put 80% of the IOPS on just 4% of the overall capacity. And lastly, I have a quick summary table of the auto-tiering technology. So on the IBM equipment, the auto-tiering technology is called Easy Tier, and that's the same whether it's the DS8000, SVC, V7000. For the EMC VMAX, the current auto-tiering technology is called Fast VP. Then on the 3 parts called Adaptive Optimization, and on the HDS, it's called Hitachi Dynamic Tiering. All of them, you can schedule the analysis period, or the period in which you want it to look at to determine the hot extents. In terms of whether or not you can influence the way it behaves, the Easy Tier and the HCT did not really give you a whole lot of things to do. The only thing you can really do is schedule the analysis period and decide if it's automatic or manual. In terms of the VMAX and the 3-part, there are some knobs to turn, and so there's some good white papers and things like that to learn how to do that. In terms of the skew curve analysis reporting, that is something that's free and available for the IBM equipment. For the EMC, you have to contact EMC, but it can be made available. For the 3-part, it's simply a matter of running a few CLI commands. And for the HCT, you need to license some tools to get that information. In this last section, we're going to look at the thin provisioning concepts. Let's take a quick look at the way thick provision volumes work. So the way that a thick provision volume works is that a host will get assigned a volume, and that volume, let's say it consists of n extents. Those n extents will be pre-allocated from the storage pool, so that when a host issues the I/O, it already has capacity reserved up to the number of extents that it has allocated. So the pool capacity will be the number of total extents in the pool minus those extents that are assigned to volumes. All right, let's take a look at how thin provisioning volumes differ. So when a host does writes to a volume, they're going to be allocated upon write. So the number of extents allocated to that volume for that host are going to be equal to the number of extents that have been written to, in this case 2. And the capacity of the storage pool will be the capacity total number of extents in the pool minus the number of extents that have actually been written to. So it's a much more efficient way to use the capacity within a storage pool on a storage controller. So let's just compare the way that thick provisioning and thin provisioning works in terms of capacity, and we'll use an example where we have 100 terabytes on 300 gig drives for the thick provisioning and 100 terabytes on the thin provisioning across 600 gig drives. So the use space on both is 30%. The allocated on the back end for the thick is 100 terabytes, and the allocated on the back end is about 40%. We'll say 30% plus some margin of safety on the thin provisioning drives. So the number of RAID groups required for the 300 gigs to cover 100 terabytes of space using 300 gig drives is approximately 50. Whereas on the thin provision side, we only need 10 because the RAID groups are much bigger and we're not using as much space. So the requirement on the thick is obviously 5 times the capacity, but is that performance capability enough? All right, let's take a look at the performance using the sample of 25,000 IOPS for both of these types of setups. So with the old way of doing things, the thick provision on 300 gig drives across 50 RAID groups, which is about 400 drives, it averaged 62.5 operations per second. There might be a few less drives because of RAID parity and whatnot, but overall, anything around 60, 70, 80 IOPS per second per drive is going to be just fine in terms of performance. Now let's look at the new way of doing things. So if we're doing thin provision and we still do 25,000 IOPS, we're going to be doing that across 10 RAID groups and 80 drives. That works out to be about 312.5 IOPS per second. That's just not going to work. So the thin provisioning is definitely going to save you capacity, but you do have to be careful not to put really I/O intensive workloads on the larger drives in a thin provision environment. And not to mention there's overhead for the system to do the thin provision management. So just to summarize the thin provisioning, using larger drives, basically with the thin provision you're going to get better storage utilization, you're going to need fewer drives, you might need faster drives. Bigger drives are going to be less expensive, but the bigger drives are going to have fewer spindles, so they're going to have lower overall throughput compared to a smaller drive in the same capacity. So in this example, when you move from the 300 gig drives to thin provisioning and you just took capacity into mind, you're just not going to have enough spindles to do the workload. And so what happens is, of course, you're going to run into performance bottlenecks. One of the ways to mitigate that is obviously to use something like SSD and auto tiering to handle the additional workload.